I want to track large data sets for training outside of Azure ML. Where should I put these things, and why is my Git administrator yelling at me right now? Welcome to this video on Azure Machine Learning. My name is Kevin Fiesel. I am the proprietor of Galaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In some of the prior videos in this Azure ML series, I included a few training files in a GitHub repository. They included 2 examples of data in the Chicago parking tickets dataset. Each file was quite small, with one being about 233 kilobytes and the other roughly 42K. I have no problem checking files of that size into a Git repository, but something to keep in mind here is that Git stores the history of your files and changes in a .git folder, meaning that if I have large files and I make changes to those files over time, that .git folder will grow and grow to the point that we might have gigabytes of data in the folder. And the worst part is that this sticks around even if we do delete the files. Git stores the history of your changes so you can revert back to a prior commit. Meaning if you accidentally check in a 500 megabyte file and then later delete that file, the history of that 500 megabyte file sticks around. There are mechanisms to remove a file or a set of files from Git history forever. The git filter branch command has been around for quite some time and can help rewrite history to remove the existence of one or more large files. But do note that it is only around for backwards compatibility at this point, and the Git maintainers do not recommend we use this. Instead, they recommend other tools. One such tool is git filter repo, a Python script which lets you rewrite history based on filters you specify. This is a good tool if you're finding yourself stuck with a mega repo thanks to someone mistakenly checking in a big file. Speaking of big files, Git also has a practical limit on how big your files ought to be. GitHub, for example, blocks files larger than 100 megabytes and even warns you at 50 megs. They also recommend keeping repositories at 1 gigabyte or smaller. These are specific to GitHub, but the reasoning behind it also makes sense for Git repos in general. If you do need to store quite large files in Git repos, I recommend Git Large File Storage, a Git extension which helps you manage large files. In practice, large file here means less than 4 gigabytes, as Git LFS for Windows chokes on files larger than that. These files are stored in a peer location, depending on which service you're using, and some implementations support writing files out to Amazon S3 or Azure Blob Storage. But regardless of which implementation you're using, at least you won't blow up your Git repo with the history of an enormous file change, and the only people who need those files will use that disk space to go grab them. So this seems like a perfectly viable solution for tracking the data files that we use for training and testing machine learning projects. But it's not quite good enough. Enter DVC. Data Version Control, or DVC, is an open source tool which allows us to track files, but in a way which makes a lot of sense for data science projects. The key behind DVC is that we are going to work with multiple iterations of a file over time. When I use the term file here, I'm being fairly generic on purpose, and that's because DVC is intended for tracking models, model weights, model metrics, and datasets. We are going to focus on datasets in today's video, but this can serve as a core tool in an on-premises machine learning project. DVC is built in Python, so you will need that installed on your machine to use the tool. The upshot to this is that it will work fine on Windows, macOS, and Linux. Now let's hop to the demo, get DVC installed, and see what it can do for us. Here we are in a PowerShell prompt. I'm in a demo repo that I've created for this video, as DVC works hand in hand with Git. The first thing I need to do is make sure DVC is installed. To do that, I'll use Chocolatey, a package manager for Windows built on top of PowerShell. If you don't have Chocolatey, I will include a link to that in the description for this video. I'll type in choco install DVC into the prompt, And then I get back a warning that I'm not in an administrator prompt, but I'm going to ignore that. If you are installing along at home, you will want to be in a PowerShell administrator prompt when you do this. But for me, I'll select yes, and I can see that DVC is installed already on my machine, so it did not need to do any work. In the worst case scenario, Chocolatey will install Python, the Visual C++ redistributable, and maybe a few more odds and ends, as well as DVC. Now that I know we have DVC installed, getting started is easy. I'm going to type in DVC space init into the prompt, which initializes a DVC repository. If I switch over to GitHub Desktop here, I can see that DVC has added 3 files to my repository. One is a git ignore file for DVC, the second is an empty configuration file, and the third is a DVC ignore file. What I'd really like to do is add some data to my project. Let's say that I have a large data set on my machine that I would like to store in Azure Blob Storage and work with locally. I'm going to copy over this parking tickets folder from my secure on-premises location and then paste it into this video demo folder. Importantly, I do not want to commit this folder into my GitHub repository, as the contents are far too large for GitHub to handle. Okay, so the contents aren't far too large for GitHub to handle, but work with me here. So the next thing I want to do is add this folder to DVC. To do that, I'll type DVC add parking tickets, and that adds the folder to tracking for DVC. What's nice about doing this is that DVC automatically adds this folder to my .gitignore file, telling GitHub to ignore the folder altogether. It also created this file called parkingtickets.dvc. This file is something I do want to check into GitHub, as it will tell other contributors on my team that the parking tickets folder should exist, just not in the Git repo. But we are going to need to put the data somewhere for other people to access it. I'm going to store all of this in Azure Blob Storage, specifically Azure Data Lake Storage Gen 2. Let's switch over now to Microsoft Azure Storage Explorer. This is a free tool Microsoft provides to allow you to interact with your Azure storage accounts. Specifically, I'll drill into my BDA Data Lake account. Inside the blob containers, I have a container called video-demo. There's nothing in this container right now, so I'd like to store parking tickets in there and use it as the remote. This is also a secured storage account, meaning I won't let the general public access it. For that reason, I need to generate a shared access signature token. These SAS tokens are good for some amount of time and allow me to narrow down who exactly is allowed to use the token. You can see on the shared access signature form that we base a SAS token on a signing key, meaning one of the account keys for my storage account. This way, I can prove that I should have this access without needing to know the actual value of the key. This is much more secure than handing your storage account keys to any random schmo. I'll set the expiration time on this token to a month from now, meaning that I'd need to generate a new token in a month if I want to continue using this process. I can also provide specific permissions. Some of these permissions are a bit confusing, so let's briefly go over them. Read is obvious. It allows you to read a blob. We obviously need that. But what about add, create, and write? Add allows us to add blocks to an append blob. So think of something like a log file that we're constantly updating. We won't use append blobs for this example, so I can ignore that permission. Create allows you to create blobs but not update them. This might be handy for some automated scripts or for immutable operations, but if we want to create or modify these files, we'll need to grant write instead. So let's do that. Delete allows us to delete blobs, something I should be able to do. List is critical for us as well, as it lets us get a listing of which blobs are available here. We can move blobs and directories to a new location with the move permission, so let's turn that on. Execute doesn't mean that we can run a script or anything like that. Instead, enabling execute means that we can get system properties and POSIX ACLs for a blob, assuming I have hierarchical namespaces turned on. I should not need this for this scenario, so let's just continue. Ownership allows me to change who owns the blobs, and permissions allows me to change permissions on a blob. Again, I won't need either of those for DVC. There are some optional parameters you can use to narrow down the scope of this SAS token further, covering things like IP address ranges and valid content types that you can upload or download, but I'll leave those alone as well. Now I can create the SAS token, and voila, we have a URL and a SAS token. I'm going to copy the SAS token to Notepad off screen, as I will need it soon. Let's close this SAS window and return to the command prompt. In the command prompt, the next thing I want to do is set a variable with my SAS token. I'll call that $SAS_token, and then paste in the value of the SAS token, including the starting question mark. This is how we'll guarantee that the user has appropriate access to this remote blob storage container. We could also save this SAS token as an environment variable and let DVC read the environment variable when it needs to. This is actually the better approach because it would allow an automated script to update that SAS token regularly and store it in a known location as an environment variable. But because I'm going to delete this repository after the video, I'd rather not keep it around as an environment variable and have to clean that up later. Now I want to add a remote destination for my data. The command for that is dvc remote add -d, and then I give the name of the remote store and its location. I'll use BDA Data Lake as the remote name. The URI we're going to use will be a little weird. It will be Azure://video-demo/parking tickets. This tells DVC that we want to use the video demo container and write results to a folder called parking tickets in that container. We don't use the URL for our account in any way, which is why I didn't have us copy it earlier. Running this was successful, though if I try to connect right now, I'd get a couple of errors, as we haven't defined the storage account name or the SAS token. So let's do that now. I'll use the command dvc remote modify -local BDA data lake to tell DVC that I want to modify settings for this BDA data lake remote data store. The first setting will be the account name, which I'll specify as BDA data lake and strike enter. That account name is the Azure storage account name. Then I'll run the same command again, this time setting the SAS token. Once we have all of this done, I can use DVC push to move these data files up. We get a message that 3 data files were pushed. And if I switch over to Microsoft Azure Storage Explorer and refresh the page, I can see that we have some files here. Let's drill into the parking tickets folder. Inside here, we have a files directory, and inside that is MD5. There are 3 files in total. One thing to note is that DVC stores data using MD5 hashes as file names, and these folders are intended to make search quicker, especially once you've been doing this for a while and have a large number of files in place. It also makes it easier to store multiple copies of the same file as you edit it over time. Each edit will generate a new MD5 hash, and so you won't have file collisions. This is great because it means we can hold on to the data as it looked at a particular time, in case we need to retrain against an older data set or prove to an auditor how we trained the model currently in production. Inside one of these folders is a file with a .dir extension. This is what DVC uses to track the actual file names and their MD5 hashes. I can download that file using Azure Storage Explorer and open it in a tool like Notepad. So let's do that and we'll take a peek inside. Once I open up this file, I can see that the structure is a JSON array with MD5 files and relative paths. That's how we convert what's in Azure Blob Storage to what we should have on premises for our parking tickets folder. Now, one more neat thing about DVC is the way it handles data modifications. If somebody else on my team has made changes to files, I can run DVC pull and get any of those changes. We can see that nobody else has made a change, which makes sense because I'm the only one doing this here. So let's make one ourselves. Before I do that, we'll make sure that we've added all of our changes to Git and then commit with the message that we are adding parking tickets to DVC. After I do that, I'll run a git push command to push these changes up to GitHub. What that does is lock in a particular commit, that is a particular point in time, and what the data files looked like. That way, if I ever need to see what the data sets looked like at a given commit, I can do so bringing that particular commit in as my baseline and pulling data from DVC. Hopefully you can see just how powerful this is for tracking data and models over time. Now I'm going to switch back to Windows Explorer, navigate to the parking tickets folder, and open up the Chicago Parking Tickets 1.csv in a tool like Notepad or Notepad++. I'll copy all of the rows from row number 2 down to the end, and then we'll save that file. Back in DVC, I can use DVC add to add the parking tickets folder and the changes that are in there, and then run DVC push to push those changes out to Azure. We can see that this time 2 files were pushed. We have the updated version of Chicago Parking Tickets 1.csv, as well as a new version of the directory file. Let's jump to Azure Storage Explorer once more. I'll make sure that I'm in the files/md5 directory and then select refresh. Now we can see 5 folders, including 2 that were just created. One of them is a block blob, which is 464 kilobytes in size. The other is our new directory file. One last thing I'd like to do is see how we can import data from Azure Blob Storage. In Windows Explorer, I'm going to do some deleting. I'll get rid of the parking tickets folder, but I will leave parkingtickets.dvc, as that's how we'll know what data to retrieve. I'll also leave the .dvc folder because that contains information on our remote data store. If you were replicating this on a brand new machine, you would have to run DVC remote add again, using the same account details and that same SAS token. We'll switch back to the command line one more time. Now I'm going to want to import data from Azure Blob Storage into my local directory. I'll use the command dvc pull, which downloads the latest form of my data. If I check the parking tickets directory, we can see the 2 files here, and it's the newest versions of these files as I have the latest iteration of parkingtickets.dvc. Again, if I were to switch back to a prior version of parkingtickets.dvc and a prior commit, and then I ran a DVC pull, I would actually get the older versions of these files. I hope you enjoyed this brief introduction to DVC and how to use it with Azure Blob Storage. This is only scratching at the surface of a really powerful tool, so if this looks interesting to you, I recommend checking out the DVC website at dvc.org and going through their tutorials. If you're really interested, leave some comments, and if I get enough comments, I'll have maybe an entire series on DVC, so let me know. We'll have links and show notes in the description below, and until we see each other in the next video, take care.